Hey science students, and welcome back to another lesson with me, Leslie from Tesla Tuition Videos. In today's lesson, we are covering the chemistry topic of ions, valency, and writing chemical formulae. Now this is definitely considered to be chemistry basics, and these skills will be really important for many other chemistry sections. Now, this section is also relevant for all physical science students, regardless of which grade you are in or which curriculum you are doing. So grab yourself a periodic table and let's get started. Right, so today we are looking at the section of ions, valency, and writing chemical formulae. So let's start with asking the question, what is an ion? Well, an ion is a charged particle. You get both positively charged ions called cations, and you get negatively charged ions called anions. The way that I remember the difference between these names of the ions is that I am quite an animal lover, so for me, dogs and cats are positive. So cats are positive, so that reminds me that cations are positively charged ions. Now for anions, the word anion kind of reminds me of the word onion, and chopping onions makes you cry, which is negative. So that helps me to remember that anions are negatively charged ions. Now, you can also describe ions as being either monoatomic or polyatomic. The prefix mono means one, and the prefix poly generally means more than one or many. So, monoatomic ions, as we see here, they consist of one atom of an element only, right? Some examples include the calcium ion Ca+2, the hydrogen ion H+, and the oxide ion O-2. Now, of course, we'll look at the charges of ions and valency in more detail later, but for now, I can just tell you that the little sign and number, that is the charge of the ion. And you can write either the number first or the sign first. So you could have also said Ca2+. That's also correct. Also, bear in mind that in chemistry, we do not show the 1. So if you see a sign without a number, such as H+, the hydrogen ion, it actually means it has a charge of +1, but we don't show the ones in chemistry. Now, the last one here is O-2. You could have written this O2-, and that is the oxide ion. And all three examples are monoatomic ions because it consists of just one atom of an element that is charged. Right. Now, for our polyatomic ions, these consist of two or more atoms grouped together where the group of atoms has an overall charge. Now, there are quite a few examples of polyatomic ions that learners are expected to know, and here are just a few examples. So, OH-, that is the hydroxide ion, where an oxygen and a hydrogen atom are grouped together, and overall it has a charge of -1. Remember, the 1 is not shown. Now, the next example, SO4-2, that is called the sulfate ion. The next example, NO3-, that is the nitrate ion. And the last example, NH4+, that is known as the ammonium ion. Now, we will talk more about polyatomic ions a bit later in the lesson when we use them to write chemical formulae, but this is just an intro to a few common polyatomic ions so that you can see that it is two or more atoms grouped together with an overall charge. Those are our polyatomic ions. Now, one of the big struggles for science learners, and it's usually in grade 10 that this happens, is that they need to learn a whole table or list of polyatomic ions. And they have to know the formulae, the charges, and the names of these polyatomic ions. Because yes, polyatomic ions do have unique names. Now, I'll put on screen now a table of polyatomic ions that high school learners are expected to know, and we will come back to this table of polyatomic ions later in the lesson as well. This table will also be attached with the documents given with today's lesson, so feel free to use that to study your polyatomic ions. Okay. So now that we know the different ways we can categorize ions as either positive or negative or monoatomic or polyatomic, now let's take a closer look at how monoatomic ions are actually formed. Right, so now we want to look at how monoatomic ions are actually formed. Now, remember that a neutral atom is not charged. It has no charge whatsoever, and neutral atoms of an element have an equal number of negative electrons and positive protons. Electrons and protons are subatomic particles that you find in atoms of elements. And if there is an equal number of negative electrons and positive protons, that is what makes an atom neutral or uncharged, in other words. Now, neutral atoms can form both positive and negative ions by either losing or gaining electrons. Remember that positive protons cannot be gained or lost from atoms because they are stuck inside the nucleus. So atoms can become charged purely because of electrons being gained or lost. Let's take a closer look. So if a neutral or uncharged atom firstly gains electrons, then it will become negatively charged because now this atom has more negative electrons than positive protons, and more negative charges than positive charges will make something negatively charged. So when the neutral atom gains electrons, it becomes a negatively charged anion. Remember, an ion is a negative ion. Here's an example. So here is the oxide ion. That is an ion of oxygen, and it has a charge of -2, which you could have written as 2-. Now, please be very careful because when you see a charge of -2, it does not mean that it lost 2 electrons. It actually means the opposite. A charge of -2 means that 2 electrons were gained, because every time you gain an electron, your charge gets more negative by 1. So if you gain 2 electrons, then you land up with a charge of -2. So a charge of -2 means 2 electrons were gained. Okay. Now, if a neutral atom loses electrons, then it means that it has more positive protons left over compared to electrons, and more positive charges compared to negative charges would make the ion positively charged. So anytime you see a positive charge, it means that electrons were lost, not gained. Please be careful. So for example, we've got the aluminium cation here, Al+3, you could have written it as 3+, and the charge of +3, it does not mean that 3 electrons were gained, it means the opposite. It means 3 electrons were lost. Because each time you lose an electron from a neutral atom, its charge gets more positive by 1. So by losing 3 electrons, the aluminium ion gets a charge of +3. So now we know that when something neutral gains electrons, it gets more negative. It gets a negative charge, in other words. And when something loses electrons, its charge becomes positive. And that explains how monoatomic ions were formed, by neutral atoms either gaining or losing electrons. So now that we know what the charge of an ion means in terms of electrons gained or lost, now let's take a look at the difference between charge and valency. Now we're going to take a look at what the difference is between charge and valency. Firstly, charge is a sign and a number. For example, +2 -3, -1, and I've put the 1 in a bracket because, as we now know, 1s are not shown in chemistry. For example, the chloride ion Cl-, its charge is -1, but we only show the minus, not the 1. Right, so charge is a sign and a number, and as we've seen, it shows us how many electrons were gained or lost. A negative charge indicates electrons were gained, and a positive charge indicates electrons were lost. Now, what about this word valency? Well, valency, technically speaking, refers more to the number in the charge, and it is a measure of how many electrons an atom wants to gain or lose. Now, for simplicity in high school science, learners can really think of charge and valency as the same thing. Although valency is really just the number in the charge, I always give the sign in any case, and yes, it's absolutely fine to think of charge and valency as the same thing and write both a sign and a number showing how many electrons were gained and lost to form a certain ion. Now we're going to take a look at how you can get the charges or valencies of elements using your periodic table. Remember, periodic tables are given to all of our students in their assessments, their tests and exams, for example, and learners must make sure that they've got a good copy of a periodic table to use for chemistry purposes. So get out your periodic table now, and let's take a closer look at how we will use that periodic table to help us get the valencies or charges of monoatomic ions. Let's take a look. Okay, so what you are seeing on screen now is a copy of a periodic table. This particular periodic table is the one provided to high school students in South Africa by the Department of Basic Education, but any copy of a periodic table should do. Now, the periodic table is a big grid of elements. It's got rows going horizontally across like this, except we don't call them rows, we call them periods. It's also got columns going vertically down like so, except we don't call them columns, we call them groups. So the rows are actually called periods going across like this, and the columns are called groups and they go vertically downwards like this. Right, now if you were to count all the columns or groups of the periodic table, you will find that there are actually 18 of them. You will see these groups are numbered 1 through to 18 at the top over here. But you will see that there is actually a more useful way of numbering the groups by leaving out these elements in the middle called the transition metals. They don't obey all the same rules as the other elements in terms of valencies, so we will leave them out and now number the groups from 1 to 8. Now, some periodic tables like mine even give the group numbers from 1 to 8 as Roman numerals going across like so. But if your own periodic table does not have the numbering of the groups from 1 to 8, you can always add it in for yourself. So with that numbering, this is group 1 with hydrogen at the top. This is group 2, skip the transition metals. This is group 3 with boron at the top. This is group 4 with carbon. This is group 5. This is group 6, group 7. And finally, the 8th group, known as the noble gases, are shown over here. Okay, now the reason you would want to number your groups this way is because elements in the same group have similarities. For example, elements in the same group will have the same charge or valency of their ions. Now, for groups 1 to 8, it is recommended that you label on your own periodic table the charge or valencies in pencil. I've labeled them in pen as this is just my personal copy, but it's recommended you label them in pencil. So when you look at those 8 groups, the charges or valencies that you will label are now as follows. For group 1, it's +1. For group 2, it's +2. For group 3, it's +3. For group 4, the charge or valency is ±4. For group 5, it is -3. For group 6, it is -2. For group 7, it is -1. And finally, the last group 8, the noble gases, they have a charge or valency of 0. Now, why do the elements have these different charges or valencies? Well, one should consider that metals, which are found more to the left of the periodic table, metals only ever lose electrons to form positive cations. So you'll see that the positive charges or valencies tend to be on the left-hand side of the periodic table. Now, hydrogen at the top of group 1, it is an exceptional element. It is a non-metal, but it forms a positive ion like the metals by losing electrons. In fact, remember the hydrogen ion H+, its valency is +1, and that tells us that the hydrogen atom lost 1 electron to form the hydrogen ion H+. Now, nonmetals, they tend to gain electrons to form negatively charged ions. And our nonmetals tend to be on the right-hand side of the periodic table, where the groups have more negative charges or valencies. Now, you might have noticed that in group 4, we've got a charge or valency of ±4. And whether you use plus or -4 depends on which element you are dealing with in group 4. For example, carbon, which is a non-metal, it can have either a charge of +4 or -4 depending on what it is bonded to. But generally, we use a charge of -4 for carbon. Now, for metals in group 4, such as Pb, which is lead, metals only form positive ions, so the metals in group 4 would have a charge of +4. Now, group 8, the noble gases, these elements are very stable and unreactive, and they do not lose or gain electrons. So they cannot form ions and they cannot become charged. So the atoms of noble gases, such as helium, neon, and argon, for example, they all have a charge or valency of 0, which shows us that they are only ever uncharged or neutral with a charge of 0. So now that we know that you can label the valencies for the 8 groups when you leave out the transition metals, now we're going to see how we use these charges or valencies to work out chemical formulae using a method known as the crossover method. Let's take a look now. Okay, so before we look at writing chemical formulae using this thing called the crossover method, let's quickly just remind ourselves how we can now use the periodic table to write the formula of an ion. It's important to be able to do this in many different parts of chemistry, including writing chemical formulae. Now, as a friendly reminder, the charges or valencies of groups 1 to 8 are as follows. For group 1, the charge or valency is +1. For group 2, it's +2. For group 3, it's +3. For group 4, it's ±4. For group 5, it's -3. For group 6, it's -2. For group 7, it's -1. And finally, for group 8, the noble gases, the charge or valency is 0. Okay, so now how do we write the formula of a specific ion? Well, you must write not only the charge, but the symbol of the element as well. So you start by firstly writing the element symbol for the ion you are dealing with, and then you use your periodic table to find the charge of that element's group, which you have hopefully labeled beforehand. Then you simply add the charge or valency to the top right-hand corner of the element symbol, and there you go. You would have written the formula of the ion. Let's do a quick example. Let's say we are asked to write the formula of the magnesium ion. The first thing you want to do is find it on your periodic table, and we'll insert an image on screen now. So the symbol of magnesium, which is in group 2, it is capital M, small g. So that's where you start. You write the symbol of the element first. Now, because magnesium is in group 2, and group 2 has a charge or valency of +2, now we know that the charge of the magnesium ion would be +2. So I now add that charge in the top right-hand corner of the symbol. But remember, it is also correct to write the number first and then the charge. So the formula of the magnesium ion, you can either write it as Mg +2 or Mg2+. Okay. Now that we are familiar with writing the formulae of ions, now let's take a closer look at how we can use this to write chemical formulae of compounds. Let's take a look. Right, so now we're going to use everything we've learned so far in the lesson to help us write the chemical formulae of a compound. Now, friendly reminder before we get started, a compound is a substance consisting of 2 or more elements bonded together. And typically with these examples, we would be given the name of a compound, and then we will use the name to help us write the chemical formula. So we're going to use a certain method that I love. It's called the crossover method, and I firmly believe it is the simplest method to get the correct chemical formula of a compound. Now, the steps will obviously make more sense once we do the actual examples, but let's first run through those steps. So step number 1 is to write the 2 ions next to each other, writing usually the positive ion first, followed by the negative ion. What do I mean by that? Well, what you would do is you would look at the name of the compound given and then decide what elements or possibly polyatomic ions are contained in the compound. And then to get the formula of the compound, you firstly write the formulae of those 2 ions in the compound next to each other. The positive ion you write first, and the negative ion you write second. And this is just part of your working out phase of finding the chemical formula of your compound. So after you have written the ion formulae next to each other, now what you're going to do in step 2 is you're going to take the numbers in each ion's charge and you're going to cross it over to the other ion's bottom corner. You don't cross over the sign, just the number in each ion's charge to the other ion's corner. Now, these numbers that were part of the charges, the numbers that you cross over, they are going to become subscripts in your chemical formula. So you might ask yourself, what is a subscript? So I've written over here, subscripts, they are the little numbers that you see in a chemical formula. And the subscript tells us the number of atoms of each element that are in a compound. For example, we've got here H2O, and the little number 2 is a subscript, and it tells us that in each molecule of H2O, there are 2 hydrogen atoms. Now, there's no number next to the oxygen symbol, and that means the subscript is 1. Remember, if you don't see a number, it means 1 because we don't show the 1s in chemistry. So the subscripts of 2 and 1 tell us that each water molecule would have 2 hydrogen atoms and 1 oxygen atom. Right. So coming back to our steps here, we've just looked at step 2, where you cross over the numbers in each ion's charge to the other ion's corner, and those little numbers will eventually become subscripts in the chemical formula. Now, step 3 is to simplify the subscripts if necessary. Now, subscripts must always be whole numbers, and usually the chemical formula gives us the simplest ratio of those subscripts. So where necessary, you can now simplify the subscripts by using a common factor. Now, finally, step 4 is to write the final chemical formula of your compound. So once again, these steps are going to make much more sense once we start getting into the examples, and that's what we'll do now. We will look at a whole bunch of different examples of writing chemical formulae, and while we go through those examples, we'll check out other rules for writing chemical formulae as well. Let's check it out. Okay, so now we're going to work through a bunch of examples where we can practice writing the chemical formulae of compounds using the crossover method. Our first example here is calcium chloride. Now, we first need to figure out what ions are we going to write for calcium chloride. It clearly has calcium in it, but the chloride actually tells us that it has an ion of chlorine as well. Please note, I've written it over here. Negative monoatomic ions of non-metals, they have names that end in "ide", and it only applies to negative monoatomic ions. The calcium ion being a metal, it will have a positive ion, but the names of positive ions, they don't change from the element's name. So calcium will have a calcium ion, but the element chlorine will have a chloride ion. So for negative monoatomic ions of non-metals, the name of that negative monoatomic ion will end in "ide". So when I see chloride, it means that, oh, this element has the monoatomic ion chlorine, but it is called the chloride ion, and it's going to be Cl-. Okay, so now we know what ions and what elements to expect in this formula. So now we have to first write the ion formulae next to each other, starting with the positive ion. Again, calcium is a metal, and metals always form positive ions. So you would look on your periodic table and find calcium, and it is in group 2. So it'll have a charge of +2, which you can write as 2+, and now we write that positive calcium ion first. So Ca+2 is the calcium ion. Next to it, we now write the negative chloride ion, which is an ion of chlorine. Now, chlorine is in group 7 of the periodic table, and group 7 elements have a charge or valency of -1. Now, for the purpose of the crossover method, during the working out phase, I show the ones in the charges. It's only your final chemical formula where you don't show the 1, but for the working out phase of chemical formulae, I do show the 1 in the charges. So I'm going to write the chloride ion formula as Cl -1, and I'm showing that 1. Now, step 2. We're going to take the number in each ion's charge, and we're going to cross it over to the other ion's bottom corner. So you leave the sign, you just cross over the number. So the 2 in the +2 charge of calcium, we're going to cross it over to chlorine's corner like that. Now the 1 in the chloride ion's charge, we're going to cross that over to the calcium corner like so. Right. So the 2 and the 1 that we cross over, they are already in their simplest ratio, so there's no simplifying of subscripts necessary here. So now we can jump to the fourth and final step, which is writing the final chemical formula. So this is going to therefore be Ca, and we cross over the 1, but then you can erase the 1 because we don't show 1s in chemistry. Then we write the Cl, and the number we crossed over to the chlorine corner is 2. And there we have it, the final chemical formula of calcium chloride. It's got 1 calcium atom and 2 chlorine atoms, and the 1 that we crossed over from the chloride ion's charge, we don't show that 1 in the final formula. No number for a subscript means 1. Okay, so that is our final chemical formula for calcium chloride. Let's move on to example 2. Okay, on to example 2. We are trying to write the chemical formula of aluminium oxide. Step 1, write the ions next to each other. Now, aluminium is going to have a positive ion because it is a metal, and we write the formula of that ion first. So the symbol of aluminium is Al, and you'll see that on the periodic table, it has a charge of +3. It's in group 3. So all group 3 elements have a charge of +3. You could have written this 3+ if you wanted to. Now, aluminium oxide, the oxide is an ion of oxygen, which is a nonmetal. So that's why it's named oxide, because it's going to be a negative monoatomic ion of the nonmetal oxygen. That's what oxide means. And oxygen as an ion, it is O-2. Remember, oxygen is in group 6, and the group 6 elements have a charge or valency of -2. So oxide, the ion of oxygen, will be O-2. So there we go. I've written our 2 ions next to each other. And now we can move on to step 2. So we take the number in each charge and we cross it over to the other corner. So the 3 in the +3 charge of aluminium, I'm going to cross that over to the oxygen corner. And the 2 in the -2 charge of oxygen, I'm going to cross it over to the aluminium corner. Now, the numbers 2 and 3 cannot be simplified further using whole numbers. And so now I can simply write the final formula of aluminium oxide. So it's going to therefore be Al, and its subscript is 2, which came from the -2 charge of oxygen, and O, and with a 3, a subscript of 3, which came from the charge of +3 from the aluminium. So the formula of aluminium oxide is Al2O3. It has 2 atoms of aluminium that go together with 3 atoms of oxygen. Let's move on now to example 3. Okay, on to example 3, where we are trying to give the chemical formula of magnesium sulfide. Now, please bear in mind that you can write the word sulfide either with a PH, or you can replace the PH with an F. So you can spell it Sulphide, but it's also correct to spell it Sulfide. So whether you write the F or the PH for the F sound in sulfide, both are correct. Okay, so firstly, we have to write the ions next to each other, starting with the positive magnesium ion. Magnesium is also a metal, so it has a positive ion. So magnesium is in group 2 of the periodic table. So it will have a charge of +2, and the formula of the magnesium ion is Mg+2, or 2+ if you prefer. Now, sulfide, the fact that the word ends in ide, IDE, means we are dealing with a negatively charged monoatomic ion of sulfur. The sulfur ion is known as sulfide. Now, sulfur is in group 6 of the periodic table, and group 6 elements have a charge or valency of -2. So we are dealing with S-2. Right. Now, in this case, we're dealing with 2 ions that have the same number in their charges. 2 and 2. It doesn't matter that they have opposite signs. Now, there is a little rule here that if the charges contain the same number, then you can cancel those same numbers to give each element or ion a subscript of 1. So before I cross over the 2's, I would notice that, oh, it's the same number 2 in each charge. So I can actually cancel them and simplify by making each charge 1, right? So now we can cross those 1's over after we've now simplified. And now we can write the final formula of magnesium sulfide. So magnesium sulfide is therefore going to have 1 magnesium and 1 sulfur. But remember, we don't show the 1's in chemistry. And so the final chemical formula would just be Mgs. The subscript is 1 and 1, but the 1's do not get shown in the final formula. And the reason we land up with 1 atom of each is because they actually both had the same number in their charges, and that means we could have cancelled those numbers to give each subscript a value of 1. So there we go. That is the formula of magnesium sulfide. Let's move on now to example 4. Okay, on to example 4, which is carbon dioxide. Now, the name of carbon dioxide should already tell us that there are 2 oxygens with the carbon because the prefix di means 2. But I want to show you in any case how we get the formula of carbon dioxide. Now, it's very much possible to have compounds that have 2 non-metals bonded together, and in those cases, you can write the order of the ions in the same order as what you see in the name. So when we figure out the formula of carbon dioxide, we'll write the carbon ion first and the oxygen ion second. We are dealing here with oxide, which means we are dealing with a negative ion of oxygen, right? So firstly, carbon. Carbon is in group 4, and the group 4 elements have a charge of either plus or minus 4, but for this purpose, I can use the charge of minus 4 for carbon. So I first write the symbol of carbon, which is the first non-metal in this compound, and I'm going to write its charge as minus 4. Now, oxygen, as we said, is in group 6, and group 6 elements have a charge of minus 2. Now, I've written another little rule here in red. Let's read it quickly. It says, note, if the numbers in the charge have a common factor, then you can simplify the numbers by dividing both by the common factor. So now if you take a look at the numbers 4 and 2, they have a common factor of 2. So I can divide both of these numbers by 2, like so and like so, and that means that I'm simplifying the numbers. So ignoring the signs and just looking at the numbers, for carbon, 4 over 2 is going to give us 2. And for oxygen, 2 over 2 is going to give us 1. Okay? So I've simplified those numbers because they have a common factor, and I divided both by the common factor of 2. So now I can cross over these simplified numbers. I can cross over the 1 to the carbon corner and the 2 to the oxygen corner. And now we can write our final formula for carbon dioxide. So it's going to be C1, but I don't show the 1 in the formula. And then O2, right? The 2 next to the O, that is the subscript that we crossed over after we simplified the charge of carbon by saying 4 over 2. And there we have it, the formula of carbon dioxide, which everyone should know by now is CO2. But potentially you didn't know where the formula of CO2 came from, and hopefully now you do. Right, so we can simplify the charges where there is a common factor. Okay, let's move on now to example 5. Right, on to example 5, which is iron 3 oxide. Now, there's a Roman numeral of 3 in this formula, and just so you know, you could have written it as just 3 lines like this. That is also a Roman numeral of 3 written in a slightly different way. So now what is going on here? Well, iron is an example of a transition metal. And just because we don't number the groups of the transition metals on the periodic table does not mean that we can't get transition metals in our examples of compounds. We most definitely can. Now, I like to think of transition metals as kind of like the rebels of the periodic table because many of them do not have one specific valency or charge. Some of them have multiple charges of ions that is possible. For example, iron, which is element symbol Fe, there is an ion of iron that has a charge of +3, as we see over here, and you also get another ion of iron that has a charge of +2. So to show the specific charge of the iron in this compound, we show it with a Roman numeral. So the Roman numeral in brackets indicates the valency or charge of a transition metal in a certain compound. So it only gives the number, so it doesn't give the sign, because all of our transition metals are indeed metals, and so students need to know that their charges are always going to be positive. I've also reiterated this point in red over here, and I said, note, the names of compounds containing transition metals have Roman numerals showing the specific valency of that metal. So the fact that they give us iron 3 oxide, that means that it contains the iron ion that is Fe plus 3. We know it has to be plus because it is a metal, and the 3 comes from the Roman numeral of 3. You could have also written this as Fe3 plus, also fine. So now we know the specific transition metal ion that we are working with, and we know that it comes from the Roman numeral. And oxide, we already know, is an ion of oxygen, and oxygen being in group 6, it has a charge or valency of -2. Okay, so now we cross over the numbers in each charge. We take the 3 in the charge of iron, and we cross it over to the oxygen corner. And we take the 2 in the charge of oxygen, and we cross it over to the iron corner. Okay, now you can't simplify the subscripts of 3 and 2, so they will stay as they are. But now we're going to write the final chemical formulae after we've crossed over those numbers to the correct places. So the final formula of iron 3 oxide, it's going to now be Fe2O3. The 2 next to iron came from the 2 in the charge of oxygen, and the 3 next to oxygen came from the charge of +3 from iron. And now we know that iron with a Roman numeral of 3 means we're dealing with a charge of +3. So for transition metals, the name has to show the specific valency of that transition metal with a Roman numeral. Let's try another example of a chemical formula that has a transition metal. Right, on to example 6. And we are given the name copper 1 bromide. This I, which you can also just write as a single vertical line, that is a Roman numeral of 1. This is because copper is also a transition metal, and you get different charges of copper ions. You get copper ions with a charge of +2, and you get copper ions with a charge of +1. So for this transition metal, copper, the particular valency or charge of 1 is given as a Roman numeral. Now we can follow our steps and use the crossover method to get the final chemical formula of copper bromide. Now, copper being a metal forms a positive ion, and we write the positive ion's formula first. So the chemical symbol of the element copper is Cu, right? And it's Cu+1. I'm showing the 1 in the working out phase of the crossover method. Now, bromide, the word ends in "ide", and that means we are dealing with an ion of bromine, which is a non-metal. Bromine is a halogen. In other words, it's part of the group 7 elements, which all have a charge or valency of -1. So the bromide ion is Br -1. Okay, so now we've got the same number in each charge, 1 and 1, but we can't really simplify the number 1 any further. So now we can cross those 1s over to the opposite corner. So the 1 in the Cu+1 charge, I cross it over to the bromine corner. And the 1 in the -1 charge of Br or bromine, I cross it over to the copper corner. That means we're going to land up with 1 atom of copper and 1 atom of bromine. But you don't write Cu1Br1, you leave the 1s out in the final chemical formula. So my final formula for copper 1 bromide is going to be CuBr. And there we have it. It has 1 atom of copper and 1 atom of bromine, and CuBr is the final formula of copper 1 bromide. Okay, so now we'll move on to some more examples, and these examples will involve polyatomic ions. Okay, now we're coming to a couple of examples that involve polyatomic ions. Now, we mentioned polyatomic ions earlier in the lesson, and we said that polyatomic ions consist of 2 or more atoms grouped together with an overall charge. Now, it's definitely tricky and a little bit daunting, but learners are expected to know a wide variety of polyatomic ions. We will put up a table of common polyatomic ions on screen now, and I'll quickly run through just a few of the many examples that you need to know. So you get things like hydroxide ion, that's OH-, nitrate ion, NO3-, nitrite ion, NO2-, sulfate, SO4-2-, sulfite, SO3-, carbonate, CO3-2-, hydronium, H3O+, and ammonium, NH4+. But there are many other examples as well. As we said earlier, I have attached with today's lesson a document containing all the important polyatomic ions that learners are expected to know. And I've written here in red as well that learners need to memorize the names, the formulae, and the charges of all the common polyatomic ions. It is expected in grades 10, 11, and 12 that learners know the names, formulae, and charges of these polyatomic ions. And you need to be able to recognize in the name of a compound whether or not it contains a polyatomic ion. It takes a bit of practice and memorization, but once you are familiar with the common polyatomic ions, it will open up a world of chemical formulae to you that you will deal with up until and including matric. Okay, right, so now we've come to example number 7, which is beryllium hydroxide. Now you need to be able to recognize that, oh, there's hydroxide in this compound, not oxide, hydroxide. And you need to know that hydroxide is the name of the polyatomic ion OH-1, or just OH-. It's not just a monoatomic oxide ion, it's a polyatomic hydroxide ion consisting of an O and an H atom bonded together with a charge of -1. Okay, now we can follow the same rules of the crossover method that we have been discussing previously, but you will see that there's going to be a new rule here that applies to polyatomic ions. Now, we start as usual by writing the formulae of the ions next to each other, starting with the positive ion first if there is a positive ion. Now, beryllium is a metal in group 2 and it has a positive charge of +2. So the beryllium ion is Be +2, or if you prefer 2+. Then, after recognizing that hydroxide is a polyatomic ion, we now write that polyatomic ion's formula, which you need to know off by heart. It's going to be OH-, and for the purpose of the crossover method, I'll write the -1 as well. Okay. Now, there is a rule with polyatomic ions that if you can see that you're going to land up with more than one polyatomic ion in the formula, you have to put that polyatomic ion in a bracket with its subscript outside the bracket. I'm going to add a quick note about that now before we go on. Great, so I've added that note about the polyatomic ion here in blue. I've said if there is more than one polyatomic ion in a compound, in other words, it has a subscript greater than 1, maybe 2 or 3, etc., then you put the polyatomic ion in a bracket with the subscript outside the bracket. If you only land up with one polyatomic ion, then you do not need to put it in a bracket in the formula. So you're going to see that we will need a bracket for our compound. And the reason for that is because when you cross over the numbers, you will cross over the 2 in the beryllium's charge of +2 to the corner of our hydroxide polyatomic ion. So we can see that we're going to land up with 2 hydroxides in this formula. So the final formula must have the OH in a bracket with the subscript of 2 on the outside. We'll see that in a moment, but we must also cross over the 1 in the -1 charge of the hydroxide polyatomic ion, that's going to get crossed over to the beryllium corner. So now what is the final formula of beryllium hydroxide going to be? Well, it's going to be Be1, the one that we crossed over, we do not show in the formula. And then we're going to have OH2. But because we're going to have two polyatomic ions, hydroxide ions, I have to put the OH in a bracket. And the 2 that was crossed over from the beryllium charge, it goes on the outside of the brackets. So when there's more than one polyatomic ion, you put it in a bracket with the subscript on the outside. So the final formula of beryllium hydroxide containing the polyatomic hydroxide ion, it is Be in a bracket, OH close bracket 2. Okay. So now let's take a look at another example that involves a polyatomic ion. Okay, on to example 8, which is called copper 2 nitrate. This compound has not only a transition metal, but also a polyatomic ion. Now, the specific copper ion we are dealing with is the Cu+2 ion. Copper, remember, is a transition metal, and in this example, we're dealing with copper that has a valency of 2. So the 2 has been indicated with a Roman numeral. You can write it like this or just 2 vertical lines, both are correct. Now, the second part of the name is nitrate, and learners need to recognize that nitrate is the name of a specific polyatomic ion. Please be so careful because this is not nitride. If it was nitride, Nitride, that would not be a polyatomic ion. That would be a monoatomic ion of nitrogen because the end of the name is IDE. So do not confuse nitride. That would be actually N-3, the formula of the monoatomic nitrogen ion. Do not confuse it with nitrate or nitrite, both of which are polyatomic ions. Nitrate in this case is NO3-, but there's a different polyatomic ion called nitrite, which is NO2-. Nitrite is a polyatomic ion, NO2-, but if this was nitride, it would not be a polyatomic ion at all. It would be a monoatomic ion of nitrogen. So one letter can make all the difference. And as we said, you really need to be able to recognize the specific names of polyatomic ions in the name of a compound. Okay, so now let's get to the steps of our crossover method. We have to first write the ions next to each other. So the positive copper metal ion, it's going to be Cu+2 or Cu2+ because of the given Roman numeral of 2. Now, nitrates, you need to know that this word refers to the following polyatomic ion, NO3-, and I'm showing the 1 for the purpose of our crossover method. The nitrate ion is a polyatomic ion, NO3-. Okay, so now we're going to go to the next step, which is to cross over the numbers in each ion's charge. So I take the 2 in the +2 charge of copper, and I cross it over to the nitrate side. And I take the 1 in the nitrate ion's charge of -1, and I cross it over to the copper side. Now, I want to show you what would happen if we don't correctly follow the rule of putting the polyatomic ion in a bracket. So I'm going to first write the incorrect formula to prove a point. Right, so this formula will have copper, Cu, and the subscripts of 1 that was crossed over, we do not show. Now, let's pretend that we forgot to put the nitrate in a bracket. We should put it in a bracket because you're going to end up with more than one of them. But let me show you what happens if you don't put it in a bracket. So you would have NO3, that's the nitrate formula. And then the 2 you cross over would be over there. And now it looks like you've written CuNO32, which is madness and nonsensical. That is not correct. You need to put the nitrate ion in a bracket because we're landing up with more than one of them. And you put the 2 from the 2 we crossed over outside the bracket. And now this formula is correct. This is the correct formula of copper 2 nitrate. It has 1 copper atom and it's got 2 polyatomic nitrate ions. We put the polyatomic ion in a bracket with the subscript of 2 on the outside. Okay, right. Let's move on now to example number 9. Right, onto example number 9, which also will involve a polyatomic ion. The name of the compound given is calcium carbonate. Now, the first step is to write the ions next to each other, starting with the positive calcium ion. Calcium is a metal in group 2, and the formula of the calcium ion is Ca plus 2, or if you prefer, Ca2 plus. Now, learners would have to recognize this word carbonate as a polyatomic ion. It has the formula CO3 minus 2. So it is a group of atoms, 1 carbon and 3 oxygens, where the group of 4 atoms together has a charge of minus 2. Now here we can follow one of the rules discussed a bit earlier, where if there is the same number in each charge, then you can cancel those numbers and make each number 1. So there's 2 and 2, so instead we'll cancel them to be 1 and 1. Now, if you can see that you're going to land up with just 1 polyatomic ion, then you do not need to put it in a bracket. So the formula will not have a bracket in this case because we're only going to land up with 1 carbonate ion. So you're going to cross those numbers over, the 1 to the carbonate side, this one also crossed over to the calcium side, and there's only 1 carbonate ion, so we don't put it in a bracket. And so the final formula of calcium carbonate is now going to be Ca1, but we don't show the 1, and CO3, and there's one of those, we don't show the 1, and we don't put it in a bracket. So ultimately, calcium carbonate has 1 calcium in it and 1 carbonate in it, where carbonate is the polyatomic ion, where there's only 1 of those in this case. So CaCO3 is calcium carbonate, and it is the compound that we actually find in seashells. Okay, let's move on to our final 10th example now. Right, so we are now moving on to our final 10th example of writing chemical formulae. Now, this one is a little bit trickier, but let me show you how to figure it out. The name of this compound is ammonium sulfate. Now, please be careful. This is ammonium, not ammonia. Ammonia, NH3, is not an ion, but rather a neutral compound. This is not ammonia. It's not NH3. Ammonium, learners need to know, is the name of a specific polyatomic ion. The formula of the ammonium ion, which you need to know off by heart, is NH4+. That is the ammonium ion, and it's a polyatomic ion. You may have noticed that the majority of polyatomic ions are negatively charged, but there are a couple of positively charged polyatomic ions that learners definitely need to know, and the ammonium ion is definitely one of them. Okay, so now I am going to add the 1 in the charge +1 just to help us with our crossover method. Now, sulfate at the end of this name, that is also a polyatomic ion. And it's true that you can get compounds with two polyatomic ions, where one is positive and the other is negative. Please bear in mind that the word sulfate can have a different correct spelling, where you replace the PH rather with an F. So you could spell sulfate S-U-L-F-A-T-E. That is the same thing, and that is also correct. So learners need to know that when you see the word sulfate, that is referring to a polyatomic ion that comes up a lot, and you need to know its formula. It is SO4 minus 2, or 2 minus if you prefer. Okay, so now we've followed the rule of putting the positive ion first and the negative ion second, but in this case, we've got two ions that are both polyatomic. The ammonium ion NH4 plus and the sulfate ion SO4 minus 2. And you recognize that those are polyatomic ions by knowing their names from the name of the compound given. Okay, so now we're going to follow the rest of our steps. Next, we're going to cross over the numbers in the charges to the opposite ion's corner. So we'll take the 1 in the ammonium ion's charge of +1 and we'll cross it over to the sulfate corner. We'll take the 2 in the sulfate ion's charge of -2 and we'll take that 2 and cross it over to the opposite corner. And there isn't a way to simplify the numbers 1 and 2, so those will be the subscripts that appear in our final chemical formula. Now remember, if you can see that you're going to land up with more than one polyatomic ion, then you have to put it in a bracket. So because we cross over the 2 of the sulfate to the ammonium ion's corner, that means we're going to land up with 2 ammonium ions in our final formula. So we have to put NH4 in a bracket with the 2 on the outside. But NH4 is also written first in the formula because it is the positive ion that must come first. So interestingly, this formula actually starts off with a bracket. You start by writing in a bracket NH4, that's the ammonium ion, and it's 2, the subscript that was crossed over, you write on the outside. If you didn't have that bracket, it would look like NH42, which is not possible. Right. Now, the next ion is SO4, and I'm only going to land up with 1 sulfate because we cross over 1 from the ammonium ion's charge. So the sulfate that we land up with only 1 of, we do not have to put it in a bracket. So we simply write SO4 like that. And there you have it. It's a pretty crazy looking formula, but that is the correct formula of ammonium sulfate. It's got 2 ammonium polyatomic ions. So we put the ammonium in a bracket, and it's got 1 sulfate polyatomic ion. The positive ammonium ion comes first in the formula, followed by the negative sulfate ion. And hopefully learners realize that although we use charges or valencies to write the chemical formulae of compounds, those charges or valencies do not appear in the final compound's formulae. There's no charges of this compound. The final compound is actually neutral with an equal number of positive and negative charges. So the final formulae of compounds does not have a charge, but we use the charges or valencies in the crossover method to help us get the correct chemical formulae. Now, we've worked through 10 examples today, but realize that there are so many other examples that you can come across in tests and exams. And for all our chemistry sections, we definitely need to be able to write chemical formulae of substances correctly. So it is essential that you practice as many examples of writing chemical formulae as you possibly can. Practice makes perfect with this topic for sure. Okay, let's finish off our lesson for today. That brings us to the end of our lesson on ions, valency, and writing chemical formulae. Now, just like with any section, practice makes perfect. So please make sure you practice as many examples as you possibly can, including those on the exercise provided with today's lesson. Keep up the good work, science students, and we'll see you on the next one.